All right, so first of all, hello everyone, I'm Antonio, and I'm going to be giving this first MDENet training session on Epsilon. We're going to go basically over the most basic bits of MDE first. I'm assuming no particular experience on model-driven engineering, first of all, given it's the first training session. So first of all, who am I? I'm a lecturer in computer science at Aston University in the UK, and I have been a committer in the open source Eclipse Epsilon project since 2011. And I've also used Epsilon myself for several approaches. I've used it to implement an automated test design and generation process. I've used it to generate websites that implement administrative processes. I've used it for serverless system introspection, and I have also used it for timetable optimization and exporting and importing those timetables to an existing system that was running in the university at the time. So again, the idea of this session is first I'm going to give some very basic concepts. I'm going to go over them. So what do we call a model? What do we call a meta model, and so on and so on. Then I'll give a very high-level view of the Epsilon project and the structure of the project and how it can be used and so on. And then we'll play around a little bit with the Epsilon playground. So just copy this link to the chat, and if you want to open it on your browser while I'm talking, that would be good, because we will be essentially using that for you to learn Epsilon. And that way you don't have to download Eclipse and start installing plugins and all that. You can just open the link and we'll start doing some things with 3, but mostly 2. And I'll go over a third example. But first we'll talk about EOL, which is one of the Epsilon languages, and it's the base expression language that is used in a lot of different parts of Epsilon. Then ETL, which is a language for transforming a model into another model. And then if we have time, hopefully, I'll give you a tour through an example of using EGL, which is a language for generating text from a model. And that text could be used for documents, could be used for diagrams, and so on and so on. So first of all, what do we understand model-driven engineering to be? So I'm just going to compare it against traditional engineering or traditional software engineering, where you are developing the system directly on the implementation language. So if you're making a website, well, you write your PHP code or your Java code and so on, right? And you're developing things in the solution language directly, in a way. What model-driven engineering is about is that you use a modeling language specific to the problem to describe or to predict, to try and describe what you're trying to do in a way that is specific to the problem. So if you're making a railway, you'll have a railway modeling language that you use. And then there will be some processes from which you may do analysis and validation and implementation and so on. But you start from that high-level description of your railway in a way. And there's a little link there to a certain blog post from the Journal of Object Technology, also on what MDE is not as well, which is it's a pretty nice read, and it's a funny read as well, because there's lots of different misconceptions that people have that MDE is UML, or MDE is code generation, or okay. And this is a bit more open than this, right? It's just this idea that we start from a high-level description of model of the system, and we use that to drive all the different tasks that we have around the system. So some basic terms in MDE. Okay, obviously we're developing a system like a railway control system. The model is describing a part of it, a certain bit that we're interested in, and we could even have like many different models from different parts of the system or different perspectives on the system. And we use a modeling language to specify the model. Okay, that's one bit that is a bit different from other uses of model, right? In this case, we have a modeling language that structures things for us. And a modeling language, most importantly, it has what we call an abstract syntax, so a set of concepts that exist in the language. So again, in the case of something like UML, you have the concept of a class, right? A set of objects. So that's a concept that you have. And then you have a concrete syntax, which is a certain notation. And the notation could be graphical, could be textual, could be tabular, any notation that you can come up with, right? So a model doesn't have to be necessarily a diagram. It can be a diagram, but it doesn't have to be a diagram. Okay, so even for things like UML, there's the usual graphical syntax for UML that people are used to, but there are also textual notations for doing UML models as well, like plantext, for instance, right? Sorry, plant UML is a textual notation for UML, and it's still UML. It's just a different notation for it. Then one thing that happens in practice is creating a modeling language tends to be quite expensive. So there are all these different bits of infrastructure that you have to provide and so on. So in the interest of sort of reducing effort and making this as cheap as possible to create a modeling language, people have created what are called meta modeling languages, which is a modeling language for creating modeling languages in a way. And what you do with a meta modeling language is you specify a meta model, and the meta model is a description of the concepts of the language. So again, if we're going back to UML, there would be some description of what a class is, right? And different parts of a class and so on, the different things you can set and different relationships between the different concepts. So in the case of the technologies that we usually use, or I'm more familiar with, it could be an XSD file if you're using something like XML schema, or it could be an eCore file if you're using something like the Eclipse modeling framework. Okay. So that gives you the abstract syntax of the language, and then you'll need some other tool to give you the notation. And that could be Sirius, it could be Xtext. So I'll just copy and paste the link in the chat. So Sirius is one tool which is quite popular for doing graphical modeling languages. And Xtext is one which is quite popular for doing textual modeling languages. Okay, obviously these are not the only ones. There are many others, but just giving some examples here. Then here are also some examples of modeling languages for different domains. So you have Archimate for your enterprise architectures. There's BPMN for business processes, Simulink if you're doing a control system, SysML if you're doing systems engineering, so systems of systems essentially. ThingML for IoT, UML for general software development. They always tend to be specific to the kind of thing that you're doing, the kind of problem that you're trying to solve. So in all of these, where is Epsilon? Where does Epsilon lay into all of this? So the idea is that a model is more than just documentation, right? This is not your usual thing when people do a UML where you do a quick sketch and then throw it away, or you do it as documentation because the client asked for it, and you do it at the end of the project because, okay, the client wants it, but we just code it the old-fashioned way, and then at the end we'll just do it. A model is something useful here, right? Because you can use the model to do AD validation on the design of your system. You can transform the model into another language because it's closer to the implementation side of things, right? So you may start with something very high level and then start to break it down, or you may actually do a transformation because you have this, it's a different compatibility layer of sorts, right? Or for instance, you could be producing reports and code from that module as well. And what Epsilon does is it gives you a family of languages that are dedicated to all the different things that you would want to do with a module. So transforming into another module, generating code, doing validation, so on and so on. It's a family of languages, basically. So Epsilon is structured in a very particular way. You can see this diagram that I've got. It looks complicated, but really it's divided into these two halves. So the top half is a set of languages, and they're all based on this common EOL language that sits at the base. And this provides the basic expression language. And then there is a number of different languages that specialize it for different tasks. So if you're going to transform your model into another module, you use ETL. If you're going to be generating code, if you're going to generate code, you would use EGL. If you're going to do validation, you would use EFL, EVL, and so on and so on. So that's one side of Epsilon. And the other side of Epsilon is what we call the Epsilon model connectivity layer. So that essentially is an adapter to allow us to use different things as models. So obviously, one of the most popular ways to do modeling in at least the academic world is to use the Eclipse modeling framework. And Epsilon has support for those models, but there are many other things that we see as a model. So you can use a MATLAB Simulink, for instance, a process as a model. You can use an XML document as a model. An Excel spreadsheet could be a model. A CSV file could be a model. Right? So we're quite open to that. And we have cases where we'll just add support for another module in the future if we consider these particularly useful for that. That's how it's structured, and now how it can be used. So the different ways to use Epsilon, the most basic thing if you're learning Epsilon is to use the playground, and that's the first link I dropped into the chat. And that's what we will be using in this session to pick up the basics. Then once you've learned the basics of Epsilon and you want to start developing solutions, we have a number of Eclipse-based editors that have syntax highlighting, and you can run the scripts directly from Eclipse and so on. So that is if you want to rapidly develop Epsilon scripts. And once you've written your Epsilon scripts, then you can embed them into your own Eclipse plugins. You can embed them into your own Java-based programs, or generally any program written in any JVM compatible language. Doesn't necessarily have to be Java. And for that, we have plain Java distributions from Maven Central. So you don't really need Eclipse to run Epsilon by itself. And we also have Ant tasks that you can integrate into your build processes. So if you wanted to just have it as one more part of your build process where some of the generated code will be produced from Epsilon, you can also do that. And we have instructions for these different things. And these slides, which I will share after this talk, they have links to different parts of the Epsilon documentation on how to use these bits. Okay. So let's move on to some hands-on exercises, and let's start with the Epsilon object language. And for this, again, we'll be using the playground. So again, EOL is the base for all the other Epsilon languages. It gives you essentially imperative code blocks. It gives you modularity. It gives you expressions. So what I'm going to ask everyone to do is to open the Epsilon playground. So open that first link that I shared. I'm just going to copy and paste it again. Okay, so just paste it again into the chat. And I'm going to ask you to open that and to select the query project plan example project. So when you go to that link, you'll see a page like this, and I'll ask you to click on the first example. So query project plan, this bit that you can see here. Right, so if you click on that, it will reload just to be sure that everyone is on the same example. I think that's actually the default one, but just I wanted to make sure that everyone is on the same page. Okay, so I think
you're saying that you see here, but you realize that you're still just sharing your slide, yeah?
Oh, that's interesting because I'm sharing my screen. Right, so it's actually just showing the window.
Well, I can see the playground.
Yeah, I can see the playground too.
Yeah,
Oh,
I can see it. Maybe
Now I can see it as well.
Oh, it had some delay apparently. Okay. Well, that's just Teams being Teams.
I think Jörn has his hand up as well. I don't know whether he wants to ask a question.
Oh, sure, go ahead.
no, that's just Teams. It's okay.
Okay. All right, so let's continue. So I'll just switch over to my slides for a moment as well, because I want to talk a little bit. But actually, I think that my next slide was going to be just talking about the UI. So let me just go over the high-level structure of the playground UI. So again, this is a playground. This is for quickly trying out different parts of Epsilon. And you'll see that the UI is divided into essentially 5 main areas. So on the left, this whole gray area, you have different examples that illustrate different parts of Epsilon. So you have all these different examples. I will be going through 3 of these. So obviously we're not going to have time to go through everything here. We'll just go through 3 of these particularly. Then on the right, you'll see that we have 4 general areas. Okay, and I'll be talking about those now. I'll just be switching back to the slides and I'll be talking about those different areas. So let me just switch over to the slides. So that was the playground UI. And let me just go through the different bits. So first of all, you'll see that there is a meta model area. And I have a little screenshot of what you will see inside that meta model area. So again, going back to the definition, these are the concepts of our domain-specific modeling language. The playground is using a textual syntax to describe a meta model called emphatic. And there's a link from the slide, which I can paste into the chat if you're interested. And what it's basically saying is, well, this is a task tracking domain-specific modeling language where you have projects that have a title, a description, they may contain a number of tasks, and they may contain a number of people. Then your tasks have a title, a start, and a duration, and they contain effort assignments. Then you have people with names, and then effort assignments have percentages, and they refer to a person. They don't contain a person, they refer a person. So that's the difference between the val that you see inside project and task, which implies containment, it's inside, and ref, which is just a reference. It's a cross-reference, right? It doesn't imply containment. So that's the description of the concepts that we have in a domain-specific modeling language. Then we have the module. And the model, again, in this case, we're using, to keep things as simple as possible in the playground, we're using FlexMe. So FlexMe is an XML, well, it actually has a JSON variant and a YAML variant and an XML variant. But here we're using the XML dialect of FlexMe to specify the actual instances of those concepts in a particular module. So for this particular project that is called Acme, we've got Alice, Bob working together to do analysis, design, and implementation. And we have a different starts and durations and percentages and all that. Okay, again, if you want more details about how FlexMe works, there's a link in the slide, which I will also paste into the chat. So we have those bits, and now there is a third bit, which is the program section. So I'm going to ask you to delete everything in the program section, paste that in, and try to click on the run button. And you should be getting the title of the first task. Okay, and what I'll do now is I'll walk you through what this very long line does. So again, if I go to the playground and I just delete everything and just paste in this for now, and I will click on the run button here, this green button with a white triangle. And if I click on that, it will take perhaps a little bit of time if it needs some warming up. Yes, of course. Yes. Oops, I didn't paste right. There we go. Okay, no worries. So once you run that, you should be getting analysis in the console. Okay. So obviously there wasn't that much going on here, but let me just go over these different bits, right? So the first bit that we have is task.all. By the way, is it okay with this font size, or shall I increase the font size? Can I increase the font size a little bit, perhaps? This is probably a bit better. Yep. So the different bits of this, right? So first of all, we obviously need to get to a task. And in order to do that, what we do is we specify the name of the type, and then we do .all to give us the set of all the instances of that type. right? So if we do task.all, you get all the tasks, and that is a collection. And there is a number of in Epsilon, all collections, they support a number of operations. One of them is first. That's just going to give you the first element of that collection. Then from that element, you can pretty much like in Java, you can do dot and the name of a field to just get the value of that field. And then we call printline, which is available for any value where we ask for that to be printed. And if you want, you can also add a certain prefix. You can give it a string to have a certain prefix before that value gets printed. So I could make it a little bit prettier by doing printline title, and it's a little bit prettier. Okay. So far, so good. Okay, if anybody has any issues running this or wants to ask anything, feel free to drop a line in the chat or raise your hand. Okay. So this is the first bit, not particularly super interesting, but just so you know the general structure of how this thing works out. And again, in the slide, there's a number of links to bits of the Epsilon documentation. So I'm just going to paste links to the sections of the Epsilon documentation where it talks about all the operations that you have available for a collection. And a collection is something like task.all. And I'll also paste the link to the operations that you have for any value, right, which includes printline among them. Okay, so if I click on this particular one, right, you'll see that any collection has a number of different methods. So I've got things like add all. I can convert between different kinds of collections. So some collections allow for duplicates, others don't, so on and so on. And there's quite a number of them. Okay, I won't be going through all of them. We'll mostly use just one or two of these in this example. The next bit, obviously, we have a number of control structures. So one of them is for, right? One of them is for, and in this case, it's a for each kind of style rather than the C style, 3 parts loop. So just do for and then element in collection, and then you'll run that piece of code, so and so. Okay. So I'll ask you if you can go ahead and try to change the code that we had so far so that it will loop through all the tasks and print the titles. Okay, and I think I'll throw that little small challenge back to you, and if you can do it in a moment. And when you've got a version, if you want to perhaps paste it into the chat. Just wanted to make sure that now people are understanding these different bits. Okay, I'll just switch back to the slide so you can use that as a reference. So if you run into issues, and so on, feel free to paste in your code. I'm happy to give you feedback on that as well. I think it's probably more useful if you try and poke at it a little bit rather than me just telling you what to write all the time. Yes, that's pretty much Corinne. Yes. So Corinne's example is right. The idea is we have a for loop, right? So obviously for and the element, in this case, is just a variable. So again, we do t in task.all. So that's the collection of things that we're looping over. And then inside there, we take this body that we had and we change these to be t.title println. And if we do that, then in a moment, we get the different titles. Okay. So obviously we have a number of different control structures. You have all the usual ones, the ifs, the elses, the switches, all those usual control structures. Now, One thing that is also quite interesting, and that kind of comes from the OCL ancestry of Epsilon, of EOL, because it is inspired on OCL, is what we call the first order operations. Okay, so say for instance that we only want to show the tasks that are longer than 3 days. And if we want to do that, we have two approaches. We could use an if inside the for loop, as usual. There's nothing particularly interesting about that. But the other more interesting and more concise approach is to use the first order operations in EOL. There's a number of them. The one that I'm going to suggest that you try and use in this session is .select. So .select, the idea is you do collection .select, and then you have a variable. This is just a variable, so you can pick any variable name here. Then you have your pipe, and then you have a condition. So this is essentially like a lambda, pretty much, if you're familiar with lambda functions from Java. So this condition would be that the duration is greater than 3. Okay. So what I'm going to ask you to do is to change the code so that it only shows the tasks longer than 3 days. Okay, and use a .select instead of an if statement. Let's see. Select iteration. Yes, Sebastian. Yes, exactly. That's one way in which you could do it, right? So I'll just come over to the playground. So the collection is task.all. So again, what we could do is we could do select, and we could do e, and then e duration. So we know it's duration from here, from the meta model, right? So we know that the task has a duration. So we do e.duration greater than 3. And if we do that, we get this, right? Now, just to say that this is actually pretty powerful, there are many other first order operations that you could use. So for instance, I could do something like, I'm just going to show you another example, where I could do task.all.collect e.title. So I could do select and just do something, where I string together a bunch of these. So I could do e duration. So I only want those. And then I'm going to do .collect, and I want the titles. And then I'll do a print line. And I'll say titles. And if I do that, I get the whole, I will get the whole list, right? So there are also these things where you can start stringing them together and doing things quite well. Sebastian, let me see, different bits. Stefan, Epsilon doesn't support implicit context in the lambdas like OCL's implicit self, right? No, it doesn't. No, it doesn't. Basically, it's this variable that you have to specify, and that's what you use inside the body of the condition. Sebastian, what is the scope for variable? Is there a name t by e here? That should be fine, because that should be just a local variable that gets added there. So there's no problem. It would just basically overwrite that or shadow that variable for now. It's essentially what happens is that we have a stack of variables, and we use the top one. So we use the top T in there. Okay. Any other questions about this bit? No worries. So again, in the slide, there's a link to the part of the Epsilon documentation that talks about all the many other first order operations you can have. And I believe, well, that's interesting. Oh, I think it's probably because I have to scroll down a bit more. Let me just go down all the way. There we go. So if you if you keep scrolling down, there is a list of all the different first order operations you can have. We have things like closures, counts of elements, if something exists, if something is true for elements, so on and so on. Okay, there are many examples of these, and they can generally be quite useful in reducing the number of loops that you have to write, especially also things like closures where you need some type of recursive function there as well. So they can be quite powerful. Now, here's another thing that you can do with Epsilon, which is quite nice, and that's called a context operation. So in this case, I'm going to give you a little bit of code. I'm just going to copy and paste this to the chat. So you should add this at the end of the program. So because in EOL, you always have normal EOL code and then a set of operations. So if you add that at the end, then instead of doing that condition that you had in the select, where you were checking the duration directly, try doing t.isLarge3. Okay, and that should now work, because what you have done is basically add to the task type. You've added a new operation. Okay, so I'm just going to ask you to make those changes and then just paste the overall program that you get by the end. Yep, so Perdita, yes, that example would be larger than 1, but obviously you could do larger than 3, larger than any number. But that's the idea, Perdita. So what we would do is, whoops, I have way too many tabs. There we go. So the idea is we go to the end, I add this operation, and then I could do things like, instead of this, I could do isLarge, and then 3. It would still do the same thing as before. All right, so I'll just drop this bit. Okay, and it will still work. Now, the interesting thing about this is, no worries. So the interesting thing about this is that you could imagine yourself having a library of these functions for your domain-specific modeling language, where you have all kinds of custom operations that you extend certain types with. And the other thing that's also interesting is, obviously, this is specific to the task, but there is support for things like essentially overriding over subtypes and so on, right? So you could have these same operations supported by multiple types here. Like I could be defining maybe isLarge for a period as well, right? And essentially just the idea that you can extend types with new operations. And this is quite useful if, again, one of the principles of Epsilon and one of the advantages of Epsilon is because we've got this base EOL language, you can create a large collection of these operations and you can reuse those across your model-to-model transformations, across your code generation, across all the different things that you do with the modules. So that's one thing I found myself, quite useful in Epsilon. And another thing that obviously you can do with EOL is you can write small imperative in place model transformations. You can make small changes to the module from inside EOL, and you don't need to involve other languages for this. So if you wanted to add a new person, you'd write code like this. I'm just going to copy and paste that into the chat. Whoops, let me just remove the formatting. There we go. So if you wanted to add a new person, you write a little bit of code like this. You would declare a new variable. So you say, well, here's a new variable called P, and it's going to be a new person. Then you set the name to Charlie. And one thing that's important is the first line, it only creates the new person. It doesn't add it to anywhere in the module. You have to be the one that decides to add it to somewhere. So here we fetch the first project of them all, and then we add this new person to the list of people of that project. Okay, so that's what we're doing in that example. So what I'm going to ask you now to do is to try writing a little bit of code to add a new testing task that takes 4 days before your for loop. And that way it should be showing in the for loop output. Okay, so if you would like to give it a try and then try pasting your code when you're done. Let's see. Let's see, so I see some people typing in the chat. The model view on the right is not being updated. I assume that's on purpose. Right, so the thing is, we aren't, whoops, let me see. The model view on the right is not being updated. Yes, so that model is the input. It's not the output of the process. So there is another example, the example I'm going to show afterwards, where we actually get to visualize the model that is produced. But in this case, the model is just an input. So it doesn't get updated when you edit it in this particular playground setup. Let's see, how are people doing? Are you running into any issues or any challenges? So remember that you need to create a new task. You need to set the title. You need to set the duration, and then you need to add it to the tasks of the project. The task. Okay. So you printed that. Yep, that's fine. Let's see. So that is almost there, but you haven't added it to the project itself. So let's just go and run this bit. Let's see how these. Let's see. You're getting it twice. Okay. Let's have a look. So you create a new task. Okay. Then you go on that bit about the title. Okay. And let's see. And no loop anymore. Okay, and let's see. Yeah, so we get design and testing. Yep. So when you say you have it twice, you mean that you see the two titles, right? Or are you seeing a different output?
I'm actually seeing the output. I'm seeing the title of my new task that I just created twice. For some reason, my pasting is not working. I must have done something stupid.
Oh. Okay.
I've gone var my new task equals new task dot title equals my testing, new task dot duration equals 4, task dot all dot add new task. And then I've got the loop as we had it before.
Ah, but that's because task dot all. Okay. Do you want to maybe share? Can you share a screenshot at least, perhaps? So task.all, that's not where you're supposed to add it. Okay, so that's an interesting thing. So you're not supposed to change task.all. That gets automatically updated when you create a new task. Okay. So as soon as you do new task, that basically goes into task.all. If you add it, then you end up getting it twice because you already had it, and then now you have it twice.
Okay, that's what's happening. Thanks.
Yep. So the way you would add it to the task is you need to find the project, and then you need to find the only project instance that you have in your module and add it to the tasks there. So the same thing that we had here, right? We have this bit where we did project.all.first.people.add. We could perhaps refactor that a little bit. So we just do proj for project. Right. I'll just put this at the top because it's just useful, and I'll make this a bit taller. So I got this is the project. This is the only project instance. So essentially this project. Then I create the task. That will automatically show up in the task.all list. So you don't have to do anything to get it in there. And the only thing I want to do is I want to add it to the tasks of the project, right? So when you create a new task, it is added to the module, but it is not added to the project yet. Okay, so that's what I'm doing in this line. I'm adding to the tasks of the project. Because one thing I could do, for instance, I'm just going to give you the difference. If I do project tasks select, right, and I run this, I get the 2. But if I forgot this bit, sorry, if I forgot this bit, if I commented out that line, then I would not get the design. All right, so obviously there is a difference between task.all, which is all the tasks in your module, regardless of where they are, and proj.tasks, which are the tasks of this particular project. Okay, is that difference clear? Any questions about this bit? Okay, all right. So let's move on. So this is as much as we needed to know of EOL for this session. And we can now move on to the next language. I see Perdita is typing something. Let me see.
No, I'm not. Teams is lying.
Oh, okay. So let's move on to the next section. So the next bit is with the Epsilon transformation language. So far, I just told you about EOL. It's the base expression language. It gives you the control structures, the ability to calculate things, print basic things, do your custom operations, and do some small changes on the module. But there will be cases when you want to produce an entirely new model from your existing module. And one language that you can use to do that, it's called ETL, the Epsilon Transformation Language. And it's for this thing that we call model-to-model transformations. The basic idea is you have this two-step process in a way, by which first you write a set of ETL rules. And the rules, what they'll do is they'll map certain types in your source modeling language to other things in the target modeling language. And the example that we're going to have is something where you go from a tree metamodel, so a metamodel that describes trees, to a metamodel that describes graphs. Right. So you have these two modeling languages, and you want to turn a tree model into a graph model. And the tree model has things according to the tree metamodel, and the graph model has things according to the graph metamodel, the graph types. Once you've written those rules, then you can basically give any module in the source modeling language. You can give that program any tree module, and it will turn it into a graph model for you. Okay, so if anyone's done formal methods, then it's basically a rewriting system in a way. Yeah? You're turning this data structure into another data structure, essentially. So let's get started with ETL. Go back to the playground and select the transform tree to graph example. So I'll close these two tabs that I've got open here. And from this list, on the left, pick the, whoops, that's my, okay, hold on. My mouse is now acting up. Well, that's interesting. I'll just transform tree to graph and see if this helps. There we go. So I just click on transform tree to graph, and you will see these different sections. So this looks a bit more complicated. I would just click on the hamburger menu, so I get a little bit more screen real estate. But you should be able to see these 6 sections here. Let's see. So if nobody has issues with this bit yet, I'll just explain what the different bits are. So again, we have the source meta model and we have the target meta model. So now we have 2. This is the meta model that describes the tree modeling language, which just has trees that have labels and have children nodes and may have a parent node. And there is the graph modeling language that has graphs, graph instances. This represents the whole graph. And then the graph has a name. And inside that graph, we may have nodes, we may have edges, and the nodes have names and the edges have sources and targets. That's what they have. And I've got the source model that is describing a tree. So I got the root node called T1, and that has 1 child, T2, and that has 2 children, T3 and T4. Okay, and I want to turn that into a graph model. So the first thing we're going to do is I'm just going to scrap this whole transformation area, and we'll start writing different bits of it. So I'll switch to the next slide. This was explaining the UI. So let's start with the most basic thing first, and I'll just copy and paste these bits. This is the only thing that you should have in the transformation section. I'm just going to paste these into the chat. Parent, children. Yes. Good catch. Right. So this bit in the source meta model that Perdita mentioned, this bit about parent and children, this is something called opposite references. So what this means is that the opposite of a of parent is children, and the opposite of children is parent. So that means that if you were to set the parent of a tree, right? If you were to get a tree object and set its parent, then you'd also be adding it to the children of its parent, if you see what I mean. So they're both linked, right? And this is something that EMF will do for you for free. You don't have to do all this, complicated mapping yourself. It's, that's pretty handy. It's a nice to have. It's not mandatory, but it's a nice to have. It really simplifies writing some of the transformations. So if you have copied and pasted that and tried running the program, what you should see is on the right, you'll see 4 little graphs showing up. Okay, so this other playground example has a picto-based visualization of the model that you get. Okay, so, and actually that visualization is internally using the next language that we'll be talking about if we have time, which is the Epsilon generation language, which will generate essentially a GraphVis specification that will get turned into this drawing. Okay, so what this rule is doing is basically saying, so first of all, every rule has a name, and this name is up to you. It's just for documentation. It's just so you know what the rule should be doing. And you always transform something. And this is the name of a variable, and this is the type. And you'll notice here that it's not just tree, it's source bang tree. And that means trees in the source model. Okay, so transform the trees in the source model to graphs in the target model. Okay, and here we also have a variable name. So with this basic rule, what we're basically saying is turn every tree into a graph. That's what we're doing in just a few lines. Okay, this is why we get 4 graphs, because we have 4 trees. Okay, that's why we're getting these results. Now, one thing that happens is obviously we don't want 4 graphs. We only want 1 graph, which should represent the root tree. Okay, so we don't want this rule to run all the time for every tree. We only want it to run for some trees. And that is what we call a guard. And this is what I'm talking about here. So I'm just going to ask you to add this little bit because it's a new bit of syntax. You'll notice that inside the braces, you can do guard and then colon, and then you can have any EOL expression there. So in this case, what we're doing is this rule should only run when the tree, does not have a parent. Okay, this is undefined operation. It's an operation that any value, even undefined values in EOL get. Okay, so this guard, what it's saying is, if you don't have a parent, if you are the root tree, then you get turned into a graph. Okay, so I would just add this little bit here. And if you just add it like this, then you'll get this big graph because it's literally the only thing in the whole module. Okay, one important bit is the guard doesn't have to be just a single expression. It can be essentially a block of code. So I could essentially do this as well. And then within that block of code, I can do anything. I could have loops, I could have conditionals, I could have local variables, and so on and so on. It doesn't have to be just an expression. But for the case when it is just an expression, then this is a little bit nicer to read. Okay, it's just a little bit of syntactic sugar here. So that's a guard. Now, the next thing that we want to do is we want to set the name of the graph to the label of the tree. So if you could just add right after the guard, inside the braces, just add the little bit of code to set the name of the graph. One important bit is it has to be after the guard line. Okay, so if you have a guard, it has to go below the guard, but still inside the braces. See, how are people doing? Yes, pretty much. Yep. So if I just do G, so again, looking at the meta model, right? I always kind of use the meta model here to sort of guide me on what I have available. So I know the graph has a name, so I do g.name. I know that the trees have labels, so I do t.label. And if I do that, then yeah, I get a graph with the little name in there. Okay. Now let's move on to the next bit. That was the rule that we had to write. And now the next thing we want to do is we want to map the rest of the trees to nodes. Yeah, I think that, okay. Yeah, that's a catch. That's an interesting catch. Yes, because it is an expression. Yes. So the next bit is let's add another rule that is going to produce nodes from trees that do have a parent. Okay, and it should be setting the name of the node to the label of the tree. So I'm going to ask you to try and write that rule, which is, it's very similar to the one you had before, but instead of producing graphs from trees that do not have a parent, you're going to produce nodes from trees that have a parent. So try doing that. It's pretty much the same kind of thing that you have to do, just changing a few things here and there. let's see. There we have so the rule from Leanne, that was that was the previous one. And then we got the one from Juan Manuel. Yes, there we go. Yes. So that's one way to, that's one way to do it. I'll bring it over and we'll see how it works. So we have this rule, I run it and I get the 3 nodes. One thing is that we also have the is defined operation as well. So instead of doing not is undefined, which is like a double negative, you can just do is defined. And it's a bit nicer. You don't end up with a double negative. Okay, so that also works, just so you know. But yes, we have that too. So that is fine. We have that rule. But obviously the main issue that we have now is that they're not connected. Right? We have the graph, we have the nodes, but they're not really connected. And we want to do that. So let's work on the next bit. The next bit is we want to extend that tree to node rule that you created to add the new node to the nodes of the graph. Okay, so again, it's kind of like in the last example that we had with EOL. You want to fetch the only target graph in the module. You want to access its nodes list, and then you want to add the node to it. And add is like the add in Java, or like the append in Python, right? So you would do .add and then give it the element. Okay, so you just need to extend the body of the tree to node rule. Let's see, this seems like it's giving people trouble. Let's see, I see Stefan typing into the chat. Yep, pretty much what Stefan typed. So let's go through different steps. So first of all, we want to get all the instances of graph in the target module. So again, instead of just typing graph, we do target bang graph. These are the .all. This is the set of all the graph instances in the target module. Then we get the first one. Then we get the nodes. Then we add the new node. Right? This is what we need to do. So if we do that and run that, now I get these nice links now, right? Because now actually the nodes are inside that graph. So I start to get these nice references between elements. So that's the containment structure that we wanted to have. But now the next thing is we want to add the child edges with equivalent. Okay, so the next thing we want to do is we want to link the new node to all its children. So we want to create edges from that node to all the nodes produced from the children of the tree. Okay. So we need to know which nodes were produced from the child trees, if you see what I mean. Okay. So you want to loop over the children, and then for each child, you want to create a new edge that goes from the node that you're producing now to the node that is going to be produced from your child. And in order to find that out, we've got something in ETL called the equivalent operation. And if you call it on a tree, it will give you the first element that is produced from it by ETL. So I'll give you some time to try to extend the tree to node rule to do this. Okay, but the most important thing is you have to use this dot equivalent thing that will give you the node that is going to be produced from that child tree. Perdita, one type of paste that I tend to do Control-Shift-V, and I will paste without formatting. I don't know if maybe that could help. Yeah, that seems to be working. Yes. Let's see. Yeah, it's a bit tricky. I tend to use Control-Shift-V a lot because I use Blackboard, and Blackboard likes to copy and paste with formatting, and absolutely produces horrible HTML. Okay. So let's see how people are doing. Did you get what you need to do, or did the equivalent bit not get across? So what you want to do is for each child tree, create a new edge that goes from the current node to the node that would be produced from the child. You see what I mean? In the chat. Let's see. Let's see how people doing. So has anyone at least got to the point where you're creating the edge? Even if you're not doing the setting of the different bands of the edge? Somebody has like a draft or something that they want me to look at, I can look at that. Because I realize that, this is the kind of leap of faith part of ETL that you have to do, and it's a bit tricky the first time you think about it. Let me see. So, tree to nodes, you create a new edge. Okay, right. So you're close, Stefan, but you're doing a parent edge. I'm asking people to do child edges, because the main thing is that, let's see, the parent equivalent. Let's try that now. Let's try that now. So you're doing the parent one, okay? So people, you're free to try and do the child one, but let's do this one. Let's try this one and see the error that you're getting, because I think that could be useful to see why you're getting that error message. Let's see. So you're getting the graph. Okay, I'll just add a graph variable here to make things a bit easier to read. So we add this to the nodes. Then you created this bit. Then you're adding the edges. Yes, and you're going with the parent equivalent. Okay, so right. So one thing that's interesting is not every parent node. Yes, so the problem is, right, if you're adding parent nodes, then that parent may not have an equivalent, because this one, right, this T1 is not going to have an equivalent, which is going to be of the right type. Because if you think about this equivalent, right, this T2 produces a node, that produces a node, that produces a node, but that produces a graph. So you're trying to assign a graph, right? You're trying to assign a graph to something that should be a node. Okay, so if you wanted to really do this, you basically have to almost check the guard again. So if T parent is defined, you would do something like this, right? Well, the thing is, you can just loop over the children. So the children is a collection, so you can just loop over it. And if you don't have any children, then you just loop over the empty collection. Yes, Juan. So that is more the sort of thing I was going for. Okay, so I just wanted to show you that you can do it with parent edges, but then it can be a bit tricky. And in this case, obviously, you get parent edges rather than child edges. So the child edges will actually have to be the other way around and so on. That was more the sort of thing I was going for, which is a lot simpler. So in this case, you are looping over the list of children. You're creating the new edge. The other bit is that we do want to add it to the list of edges of the graph. Okay, that's the one bit that was missing. And if we do that, whoops. Oh yes, I should the edge. Right, then we get this. Okay, so in this case, you see that we have the graph, the nodes. We have created two edges, and one edge goes from T2 to T3. So T3 is a child of T2. And one goes from T2 to, well, this is slightly obscured because of the feedback section. Let me just do this bit. And one goes from T2 to T4. Okay, and we have this bit here. Okay. Now T1 is the root. Right, T1 is T1 is the root. So T1 is not producing. There's no links that go from T1 to T2, right? So we're missing that bit. So in this case, we probably have to do something of the sort here, where we also add children edges, right? But actually, the edges are always from between nodes, right? So we can't really do one from the graph. Yeah. So we just do from these T2 and T3 and T4. These are the ones that we have, okay? Because the T1 is just a graph. Okay, so the trick here, this equivalent bit, right? That's a little bit of magic in a way that ETL gives you, that basically says, give me the thing that is going to be produced from tree. And there's a number of different versions of this equivalent operation. So equivalent without the s at the end is just give me the first element that is produced from the source element. And the first one that gets produced, because in this case, we're always going through the children, it's always going to be something produced by these tree to node rule. So we know it's going to be a node. Okay. If we had done parent edges, then we kind of run into this situation where you have a certain guard that you have to be careful with and so on. Obviously, it could be that the same element could be producing the same source model element, could be producing many model elements. And in that case, you would want to, if you wanted to get the set of all the things that are produced from this model element, then you would use something like equivalent with an S at the end. That will give you the full list of everything that gets produced from this source element. And in there, you basically have to pick the first one. Right, so I could write it this way as well. I could write equivalence dot first, and that would also work. Okay. I could even specify the name of the rule that I want to get the elements from, because I say, well, I only want the equivalence produced by this rule specifically. So I could say I only want the equivalence produced by that very rule. And I could further specify this, and I would, essentially get the same thing here. I see Juan is typing. Let's see. All right. Okay. Never mind. So I could have also done that. Now, because the case of something equivalent is so common in Epsilon, in ETL, there's a special syntax, which is a shorthand for this. So I could do this special assignment, and that is equivalent to assign the equivalent of tree to edge.target. Right? So there's a little nice shorthand that you can also use, which helps with the readability so long as you know what this special assignment is doing. Okay, there's a little bit of syntactic sugar there in case you want to use it. So that was essentially the rule, and I've got the source code here in the slide in case you want to go back to this. Okay. But obviously there is far more to ETL than what we have covered in this presentation. So we haven't gone over all the different ways in which you can do rule scheduling. We haven't talked about primary rules and lazy rules and greedy rules. We haven't talked about, actually we did talk about that special operator. We haven't talked about rule inheritance, overriding, using the transformation traces to keep links from the source elements to the target elements. We haven't had time for everything. Okay, maybe this is something that we could be explored in follow-up sessions. But just so you know that there is more to ETL than just this basic bit. But in general, you see that it's a dedicated language specifically for turning models in this modeling language to models in this other modeling language. Okay, now let's go into the third and last language that we'll be able to cover in this session. Given that we only have 10 minutes, I'll just give you a walkthrough over the example and sort of explain what the example is doing. Okay, but we won't have time to do hands-on bits for this. So it's an example again of EGL. EGL is the Epsilon generation language, which implements model-to-text transformations. And that means, yes, it means code, but it also means reports. It could mean images. If you're using some kind of textual notation for diagramming, like GraphViz, you could do that. And in fact, that is how Picto works. That is essentially how this visualization that you saw in the playground works. Right? It uses EGL to produce a GraphViz description that then gets rendered into SVG. So you can do it with EGL just fine. And EGL at its core is essentially a templating language. It's very much in the style of Twig or Jinja or raw PHP. If you've done like old-fashioned PHP websites without a framework, right? It's kind of like in that style. So I'll just go and switch to another playground example called the generate effort table example. And I'll just switch over to that and I'll explain what the different bits do. So in this example, we have the same task project and task meta model from the last time. So our projects with our tasks, with our people, with our effort assignments. And we have the same model with the Acme project, Alice and Bob working on analysis, design, and implementation. But now on the left, instead of having something that produces a model, I have something that produces HTML. And again, if you use any type of template-based language, it's quite similar. So if I want to have some static HTML, I will just include it as the template. And when I want to start generating bits and have dynamic sections of that document, I'll start adding these bits with square brackets and percentages. And inside there, I can add any arbitrary EOL code. So that means I could have loops. I could have calls to functions. I could have operations, anything you can do in EOL. So in this case, what we're doing is we're generating a bit of HTML with a link to Bootstrap, the Bootstrap CSS bits. Then we're starting a table. We're using some bits of Bootstrap to make sure it's striped. Then we're generating the header row, and I've got an empty cell there. And now I will have one more cell per person. And you'll notice that there's this bit here, which has the square bracket percentage equals. So this essentially allows you to just print out the value of a certain expression. So just print out the name of that person here. And I have a header row with all the people. And then I have another one where I'm going to have a row per task. And for each task, I'm going to print out the title. And I'm also going to print out the percentage of that person is contributing to. And you'll see here that there's a slightly different first order operation called select one, where instead of selecting all the ones that meet the condition, you select the first one that meets the condition. And you'll also see there's this question mark dot operator. So that is that's the Elvis operator in a way, which what it does, it's Elvis because it kind of looks like the 2P of Elvis. But what this means is if there is such a person, then access its percentage. If there is no such person, then just return a null value. Okay, so it's kind of like a save dereferencing operator, which will always work no matter if there is a person or not. Then if there is such a person, we'll get the percentage and we'll show it. Otherwise, if the person does not exist, we'll just give 0%. Okay. And then when we run that, we'll get the HTML, right? And this HTML will look as you see here. Right. So you see that this is really just a thin layer on top of EOL, where you have bits of template text and bits of EOL code, right? And it's a nice layer on top of EGL. And the same way you'd be producing here HTML, you'd be producing any other kind of textual representation here. One thing is that EGL comes with many more features. You can have protected regions, for instance, that could be customized by a developer and then kept across regenerations. So this is very commonly done for code, where you say, well, all these bits have been automatically generated. You should not be changing this. But here's a bit where you can introduce your own customizations to the logic, or your own functions or your own methods if you're producing something like a Java class, for instance. There's also support for what we call formatters, which are for things like automatic indentation. So say, for instance, if you're producing Java code and you want the code to be nicely indented, instead of you doing the indentation in the template, which can really make it very annoying to write, difficult to maintain, you can just have a formatter do a post-processing step in which it will do the indentation for you. And for instance, I did one for SQL, which it will do indentation based on subqueries. And it's just basically extending a Java class, telling it this is when you should indent and this is when you should de-indent, and that's it. So there are some bits that EGL, nice bits that EGL has. And there is also a language called EGX, which is a coordination language for model-to-text transformations, which is linked from the slides. And I'll just drop a link here. And this is designed to allow you to, from one execution, generate a whole tree of files, possibly using different templates. I believe there's an example here where you could say something like, I'll just give you an example. This is, I think, a bit too, okay, it's almost a bit too complicated, but the idea is, for instance, that if you had a library model, right, you could basically turn every book in the library. You could generate text from every book in the library by going through the contents of the model and so on, okay? We don't have time to go into the details of this, but essentially, if you need to produce not just one file, but a whole tree of files, you might end up using the EGX language to orchestrate the use of all these templates. And that is almost it. Just going through things, just a quick recap. So we talked about Epsilon, we introduced the basic concepts, and we talked about how Epsilon was divided into a family of languages and a family of ways to understand different modeling frameworks, essentially. Then we talked about the EOL as the base expression language. We talked about ETL as a language to do model-to-model transformations. And we talked about just briefly went over an example with EGL, where we were rendering a HTML from a module. And that is pretty much it for this session. Thank you, everyone.